Ayan, it's 3 o'clock already.
Yes, yeah. So I welcome all of you. Hello, and
Yes.
I welcome all of you to the first Bibha Chowdhuri Memorial Lecture that the Department of Physical Sciences, IISA Kolkata, is organizing. And I'm really proud to be part of this occasion where our first speaker is none other but the illustrious Professor Ashoke Sen, who is probably one of the brightest stars in the sky of Indian science at the moment. And we are also very happy that we have termed this memorial lecture, which we will organize regularly now, perhaps even like once a semester, uh, in the name of one person who is a pioneer in science research in the country, because she was the first PhD in physics who was also a woman. So this is something that is still an issue in Indian science, as most students, most practitioners of the field are aware of and actually lament, because we still have, this is the time of inclusiveness and we want equality. Gender equality is probably one of the biggest challenges that we face. And yet we really do not have enough women physicist students as well in the country, as we always see even at IISA Kolkata, that there is a big skew in the ratio of male and work in a time when society itself was completely patriarchal. And in spite of all the odds that surmounted her, she came out and did internationally competitive work. Of course, the work was probably lauded later, but it was lauded nonetheless, where she actually has a star named after her. So I will not go into too much of details about Professor Chowdhury or Professor Sen either, but I would now leave you with our Dean of Faculty Affairs, who also happens to be a physicist and one of our most senior and esteemed ones, one who knows Professor Sen really personally, none other than Professor Bishwar Mukhopadhyay, whom I now request to take over and introduce and speak a few lines about Professor Chowdhury as well as Professor Sen. So over to you, Professor Mukhopadhyay.
Thank you and welcome everybody. Now, Professor Ayan Banerjee has already kind of laid out the social or socio-cultural backdrop of Professor Bibha Chowdhury's functioning as a physicist and sort of indicated how her prevailing circumstances might have provided impediments to her achievement. Probably the achievement can be understood if in this backdrop, her actual career profile is quickly recounted. She studied in Calcutta University, being probably the loner physics student who was a woman, then worked in Bose Institute, Calcutta, then went and had her PhD from the University of Manchester in a very renowned group led by PMS Blackett, later got associated with Tata Institute of Fundamental Research and later this Physical Research Laboratory at Ahmedabad, before she returned to Calcutta towards the later parts of her life. Now, while in Calcutta itself, working with probably Professor D.M. Bose, Bibha Chowdhury participated in a series of papers published in Nature. And these were works which included, among other things, which suggested methods of reconstructing the momenta of charged particles occurring in cosmic rays or subnuclear charged particles in cosmic rays. And such techniques suggested and developed by them had to play a considerable role in the discovery of subatomic particles in cosmic rays, including the pion, the lightest meson, or lightest strongly interacting subnuclear particle. So the fact that Professor Chowdhury, in spite of the potential impediments, became part of all that requires much more mention in our community than we already have it. Now, a fitting tribute to her achievement and her memory is hopefully going to be provided today with one of the most internationally renowned physicists of our time speaking on the occasion of her memorial lecture. Professor Ashoke Sen, now in International Center for Theoretical Sciences in Bangalore, and earlier for a long time, Harish Chandra Research Institute, Allahabad, and even earlier with Tata Institute of Fundamental Research in Bombay, he doesn't need any more introduction. He is internationally renowned for his pioneering contributions in string theory and a few related areas like cosmology and particle physics. So, in a way, he is going to speak about a lady who was a forerunner in Indian science as far as experimental high energy physics goes. I won't waste any time talking about Professor Ashoke Sen's career profile and the numerous awards and recognitions he has won. He has won. That is part of our folklore now. Let me, before inviting him, just say two things, which I have said in other forums also. And these I can say by after having an association with him in the same institute for nearly 25 years. First, it is wrong to say that Ashoke Sen is a great string theorist. A much more correct statement is Professor Ashoke Sen is a great physicist, as is reflected in his insight revealed in across the board in subdisciplines of physics, including starting from cosmology to statistical mechanics to electronics. And secondly, having worked in the same institute with him for nearly 2.5 decades, I could say that it is practically impossible for a practicing physicist to stay within, for some time, within a few hundred meters of Ashok and not be influenced by his insight or not being illuminated by him. So I think that says enough, and I'm sure all his colleagues, me being just a rather insignificant sample, all his colleagues will completely testify to this fact. This said, I think we should have the lecture now. Before that, I just want to remind the audience of a couple of things. First, please keep yourselves muted throughout, and questions will be taken only at the end of the lecture. Please type your questions in the chat box, and myself or other organizers will take turn in pointing out or reading out the questions, and Professor Sen will reply. This said, I think it's not the occasion to applaud online, but I can hear in my own ears a thunderous applause as Professor Ashoke Sen starts his lecture. Ashok da.
Okay, thank you, Vishnu, for the very kind introduction. Let me share my screen. Can you see my screen?
Yes. Can
Okay.
it be made full? Yes, exactly. Perfect.
So it's a great honor for me to be giving the Bibha Chowdhuri Memorial Lecture. As you heard from Vishnu, she worked in particle physics, which many people consider as esoteric subject with possibly few applications to practical life. I work in an extreme spectrum of string theory of particle physics, which is a subject called string theory, and that's considered even more esoteric even by particle physicists. Nevertheless, what I'll try to discuss in this talk is that even these esoteric subjects may have significant impact on the future of our universe. And that will be the subject of this talk. So the story that I'll be telling you about begins about 100 years ago, when Hubble discovered that our universe is expanding. And it's expanding in all directions uniformly. So far away objects are moving away from us, and further away they are, the more is their speed. And this is nothing special about us. From any point in the universe, it's the same story, that every object is moving away from every other object. And this state of the universe can be understood as a particular solution to Einstein's equation for gravity, which is also called the general theory of relativity. And the theory of expanding universe has come to be known as the Big Bang theory. And this was confirmed by the discovery of cosmic microwave background radiation in the 1960s. This is the thermal radiation at 2.73 Kelvin that fills the entire universe. And this is believed to be the relic of the hot radiation that existed in the past, but is cooling down due to the expansion of the universe. So by the middle of 1990s, we had a good understanding of this theory. And what was generally believed is that the universe contains three kinds of sources of energy or mass density. And in this talk, I'll be using energy and mass on equal footing because of this Einstein's relation E equal to mc squared. So energy is the same as mass and vice versa. So what was thought is that the universe consisted of ordinary matter like stars, interstellar dust, etc. Then it was also known that ordinary matter cannot explain what we see in terms of expansion of the universe. So we need also some unusual kind of matter, which we call the dark matter. This is an unknown source. We still don't know what dark matter is. Nevertheless, what's important for us is that it behaves as ordinary matter as far as Einstein's equations are concerned. And then there is, of course, the cosmic microwave background radiation. But this has a very small effect at present, but it was important in the past. And so the idea was that the explosion, which was at the beginning of time, set the universe expanding. But because gravity is attractive, it was believed that the pool of matter will be slowing down the rate of expansion of the universe. Okay, so even though the universe is expanding, the expansion rate should be slowing down with time. That is what we understood in the middle of 1990s. But in 1998, two independent experiments made a profound discovery. Both experiments studied supernova, or how, more precisely, how fast they are moving away from us. And what they found as a result of this study is that the expansion of the universe is in fact accelerating instead of slowing down. And this is impossible to explain if the universe is made of ordinary matter and radiation like what we thought in the middle of 1990s. So the best explanation for this phenomenon that is available today is that 73% of the energy density in our universe exists in an unusual form, which is known as the dark energy. It's also called the cosmological constant. Okay? In fact, this form of energy was postulated by Einstein almost immediately after the discovery of general relativity. But then, since there was no experimental evidence for it, he gave up that idea. But that seems to be the best candidate for why the universe is having accelerated expansion. And the essential point is that this kind of matter, the dark energy, has negative pressure. And this negative pressure causes gravity to act as a repulsive force instead of an attractive force. The remaining 27% is mostly made of ordinary matter and dark matter. And an insignificant fraction is in the cosmic microwave background radiation. So dark energy has now become almost a household word, at least among the scientists. But what is perhaps not widely appreciated, even among the scientists, is how the discovery of dark energy has changed our perspective on the future of the universe. And today's talk will be the story of the future of the universe. And hopefully this is also going to be the story of our future, provided we survive pandemics, nuclear war, and any other exciting event that may occur on the way. So this story will be divided into two parts. Okay, the first part will be the classical story, where you ignore the effect of quantum mechanics and just study what would happen if universe followed the laws of classical physics. And then in the second part, I'll describe what the quantum effect, what are the consequences of quantum theory. Now, as I've already told you, presence of dark energy causes the universe to undergo an accelerated expansion. And this is an inevitable consequence of Einstein's general theory of relativity. Once you postulate the presence of dark energy, okay, with negative pressure, then this will automatically follow. Furthermore, one can show, again as a consequence of Einstein's equations, the dark energy density remains constant as the universe expands, unlike ordinary matter, which gets diluted. But this is what common sense will tell you, okay? Because if you have a certain amount of matter and if the universe is expanding, then the amount of matter per unit volume should be going down, okay? So the density of matter will fall. And this is indeed true for ordinary matter and dark matter. But dark energy, because of this negative pressure, okay, what happens is that as the universe is expanding, this negative pressure, okay, unlike the expansion of a gas where expansion causes it to lose energy because it's doing some work, okay, because of the negative pressure, it gains energy in that process. Okay, and the gain in energy precisely balances the loss in the density that will get because of the expansion. Okay, and one can show that the dark energy density actually remains constant. And this means that the acceleration that we see today is going to continue in the future, because the acceleration is caused due to the presence of the dark energy density, and the dark energy density is not going away anywhere. And one can estimate that in the future, the size of the universe will double in about 12 billion years. So because of this accelerated expansion, it turns out that it's physically impossible for us to reach very far away places in the universe. In particular, even if we manage to travel at the speed of light, okay, which of course we cannot do, but we can send out a light signal and see how far we can reach. We can reach objects which are at most at a distance of 18 billion light years from us today. Okay, this is something that you can calculate based on present understanding of the expansion of the universe. So what about objects that are further than this? So the point is that the objects further than this are moving away so fast that even light cannot reach them. And technically we say that these objects that are further than 18 billion light years from us are outside our horizon. Furthermore, as the universe expands, more and more objects will go out of our horizon, because more and more objects are going to go further than 18 billion light years from us today, and then they'll fall out of our horizon. We can never reach them. So it's as if the universe becomes a multiverse. It becomes multiple universes that cannot communicate, even though between these universes there is no physical boundary. Okay, there is nothing, no wall which tells us that this is the place that you cannot cross. It's just that from any given point, okay, if you send out light signal, which is the fastest possible traveler, you cannot reach beyond 18 billion light years. Now this sounds like a science fiction. Okay, if there is no boundary, how is it that we cannot reach far away places? But it's a reality. Okay, and it's a reality that we can actually experimentally verify, because at present the part of the universe that we can see has a radius of about 46 billion light years. In particular, the cosmic microwave background radiation that we are seeing today is coming from points in the universe which are at that distance from us today. But so this is larger than the present horizon. Okay, I told you already that presently we can travel at most 18 billion light years from us. So many of these points, many of the regions of the visible universe are actually unreachable. Okay, even if we try hard enough, okay, it's theoretically impossible to reach those regions. So just based on this observation, we can see that the observed universe has already split into more than 15 parts that cannot communicate with each other. Okay, this 15, the number I got just by taking the cube of this number, right? Because if in terms of size, it's 2.5 times. In terms of volume, it will be cube of that. So the observed universe, okay, the part of the universe that we can see using CMB, cosmic microwave background radiation, already has 15 separate parts, okay, that cannot communicate with each other. In fact, the actual size of the universe is likely to be much bigger. Okay, this is, we can see up to 46 billion light years, but we believe that the actual universe extends far beyond that. And so it contains a large number of parts that cannot communicate. Now, before I go on, I'll give some technical details. Many of these will not be really necessary for following the rest of the talk, but it will be useful for following the talk. So it will give you a better insight into what's happening. So if you recall, in special theory of relativity, we learned that all inertial frames are equivalent. The laws of physics do not change if you move at constant speed. And we also learned that for events that take place at different points in space, there is no well-defined notion of simultaneity. If in some inertial frame, it looks like the two events are occurring at the same time, then a different inertial frame, the two events may look like as if they're occurring at different times. Now, it's not that the special theory of relativity is wrong, but in an expanding universe, a different perspective is a little more useful. So in an expanding universe, it turns out that we have spatial choice of frames, and those spatial choice of frames are characterized by the fact that in those frames, the cosmic microwave background radiation looks isotropic. It looks the same, okay, the radiation coming from all different angles look the same. And these are called co-moving frames. If we are in a different frame which travels with respect to a co-moving frame at constant speed, in that frame, the cosmic microwave background radiation will not look isotropic. In fact, because of the Doppler shift, the photons that are coming opposite to the velocity will look like having higher temperature than the photons which are coming from behind you. So the co-moving frames are important because it turns out that the stars, planets, galaxies that you see in the universe are all nearly co-moving, which basically means that their speed relative to co-moving frame is small compared to the speed of light c. So whenever we talk about low speed, okay, it's always measured with respect to speed of light. The second definition that is going to be useful is that given two far away events, in special relativity, as I said, you cannot say whether they're simultaneous or not. But in an expanding universe like ours, there is a notion that we can use for saying whether they're simultaneous or not. And that is that we say that they are at the same time, t, if they occur at the same value of the CMBR temperature. Imagine that some event A takes place here, some event B takes place there. As long as the event takes place, okay, at the same value of the CMBR temperature, we say that they are simultaneous. And this definition makes sense that because CMBR temperature is actually falling with time. This time t is also the proper time of a co-moving object. Now, another point, which is even more technical that I like to note here anyway, is that these definitions are somewhat approximate because CMBR itself has some local fluctuations. It's not absolutely uniform. Okay? But that small fluctuation is not going to play a role in our talk today. Okay. Now, this slide is perhaps the most technical slide. And as I said, you don't really need to understand this to follow most of the rest of the talk. But it gives you a very useful view of the entire universe, entire history of the universe. So I'll try to spend some time explaining what this diagram means. So in this diagram, the vertical direction represents time. But what we plot along the vertical axis is not exactly time, but it's a function of time. T is the cosmic time. Okay, that's the proper time of the co-moving observer that is fixed by the CMBR temperature. So this capital T is some function of this time. Okay, it's a complicated function, but it's a known function. At late time, okay, when for large T, the function this capital T takes this form. So you see that as the small t, okay, the physical time goes to infinity, the capital T actually goes to 0. Okay, so this is the end of the universe. There is really no end, okay, because this corresponds to small t, the actual physical time going to infinity. But in this coordinate system, it looks like the universe has an end at capital T equal to 0. This one is the beginning of the universe. And this is us. Okay, that's the way I have brought it. This is today. This is the time T equal to T naught, that is today. Now, what are we plotting on along the real axis, along the horizontal axis? Along the horizontal axis, what we are plotting is the distance from us. But again, it's not quite the distance. It's the physical distance is given by the value of r times again a known function, okay, which I'm calling g of t. Okay, and g of t and f of t are related. I'll not discuss that any further here. But what's going to be important is the late time behavior. Okay, for large time, okay, in the far future, this function g of t has this exponential form. Now, this function f of t and g of t are chosen spatially, okay, and that spatial property that this diagram has is that light travels at 45-degree angle with the particle from any point and any time. If you send out a light signal, it will travel at 45-degree angle with the particle. Massive objects travel at a speed that is lower than that of light. So massive objects travel at less than 45-degree angle with the particle. And co-moving objects, stars, planets, galaxies like us, they travel along the particle. So I have drawn this so that this is us. Okay, we are co-moving, so you'll go along the vertical axis. Now I place stars at the center, but there's nothing special about this. It's like drawing a map, right? When you draw a map, you always place your country at the center. So it's like this. Okay, even though there is nothing special about us. Okay, I have drawn this map so that we are at the center. So you go up like this. Now, so this means that this is where we are today. Right? This is our trajectory, and this is today time. So this is where we are today. Now let's see what will happen if you send out a light signal. Since light travels at 45-degree, a light signal that is sent out from us today will travel along these 45-degree angles. And we can see that they can reach up to a limited distance, right? Because a point here, okay, another co-moving object which is going up here, can never be reached by us because we are limited within this cone. Okay, any massive object will travel at less than 45-degree with the particle, so it will have to be confined within this cone. And this diagram illustrates nicely the notion of horizon. We see that there is a distance that we can define, so that even if we try hard enough, we can never reach co-moving objects that are outside this distance. Okay, that is our horizon. So this distance is what we call 18 billion light years. The past horizon, okay, or how far we can see, also can be seen from this diagram. We simply have to draw the 45-degree angle light lines backward, because light will reach us along these 45-degree angles. So you see that the part of the universe that we can see is this part over here. This is the radius of the part of the universe that we can see today, right? Because the light from this far distance can actually reach us today. And the claim that I made is that this distance is about 45 billion light years, which is larger than this distance that we can access today. But this diagram also illustrates something else, which is that you can see that as time proceeds, it looks like that our horizon size becomes smaller and smaller. Because, for example, when you are here, we can access only a small part of the universe, okay, only this distance. Now that sounds strange. It sounds strange because that's the way the diagram is plotted. Okay. So the point is, this, even though this looks like a smaller distance than what we can access today, okay, remember that this r is not the physical distance. To get the physical distance, you have to multiply by this function g of t. Okay. And when you do that, you find that this physically, actually, this distance is more or less the same as this distance. Okay, so the physical horizon size doesn't go down. Okay. But we see that many of the objects that we can access today, if we try, for example, a co-moving object that is going like this is within our horizon. We can send out a spaceship and reach this object. But if we try to reach the same object at a later time, it's impossible. Okay, because we can never reach that object, okay, if we try here. And that's the statement that with time, more and more objects are going out of our horizon. Okay, so in this diagram, that's the way we understand it. So anyway, as I said, this diagram is not going to be essential for following the rest of the talk, but at some point I'll make use of this again. So let's now get back to our story. So what we have said is that the expansion of the universe is pulling co-moving objects apart, and slowly they are falling out of each other's horizon. But this doesn't mean that it will actually pull our galaxy apart. Okay, the Milky Way galaxy in which you are living is not going to be torn apart by the expansion of the universe. And the reason is that the Milky Way galaxy is held together by the local gravitational force between the constituents, and that local gravitational force between the constituents is strong enough to overcome the overall expansion of the universe. So given this, one can ask, what about other galaxies? So our nearest large galaxy is Andromeda, but Andromeda in fact is at present moving towards us. And based on simulation, one finds that it's expected to merge with the Milky Way in about 10 billion years from now. So even the Andromeda is not going to be torn apart from us. But besides these two large galaxies, Milky Way and Andromeda, most other galaxies that we can see today and that where we can reach today will eventually go out of our horizon. Before they go out of our horizon, it's in principle possible for us to establish civilizations in those galaxies. But afterwards, as the universe evolves, we'll lose touch with them forever. Okay, not just because of the practical difficulty, but even theoretically, it will not be possible to communicate with those other civilizations which we might establish in those other galaxies. So in the far future, our local group of galaxies will be the only one that will be within our horizon. And when the last star in that galaxy dies, then life in the current form will not be possible, even though there are various ideas of how you might extend life. But this is expected to happen over a period of 10 to the 13 to 10 to the 14 years. And this will be a somewhat sad and lonely end to our civilization, because we will eventually end our civilization and there will be nobody to communicate with. We'll see that in the quantum world, life will perhaps be a bit sadder, but it will definitely be more exciting and adventurous. So this is the end of the classical story, and now I'm going to move to the effect of quantum mechanics, quantum theory on the future of our universe. So the quantum story begins with that of a particle that slides on a hill. So from everyday experience, we know that if you have a hill with two valleys, then the particle can come to rest either at the bottom or at this valley or at this valley. And if we leave the particle at A, for example, then the everyday experience tells us that it will continue to rest at A forever unless we disturb it. But once we take into account the effect of quantum theory, one finds that there is a tiny probability that the particle will disappear from here and appear on the other side of the hill. This is sometimes called the quantum tunneling. And once it appears on the other side of the hill, it can of course roll down to B. This probability is small, but it's non-zero. Okay, such a thing can in principle happen in quantum theory. Now, our interest, of course, is not in a particle, but we are interested in the whole universe. And the dynamics of the universe is described not by the dynamics of particles, but what is called the dynamics of quantum field theory. So quantum field theory, of course, is a somewhat technical word. But let me just say that for the purpose of this talk, we can regard a field is like having a particle at every point in space. Imagine that we have placed a particle in every point in space. And imagine also that these particles are moving in some hidden directions. Okay, they are fixed in space, but they move in some hidden directions, which you cannot see. So let me give a familiar example. Okay, it's a magnetic field. Okay. So you know that magnetic field has three components, Bx, By, and Bz. So if you want to specify a magnetic field, you have to give the value of Bx, By, and Bz at every point in space. But you can also think of this is as if there is a particle at every point in space, and Bx, By, and Bz describe the coordinates of the particle in some hidden direction. Okay, it's just an analogy. This is just a way to think of magnetic field. Okay, as if you have placed a particle at every point in space, and these are the coordinates of the particle in some hidden directions. Now, the magnetic field is not the simplest possible field you can imagine. The simplest possible field that you can imagine is called a scalar field. So what's the difference? Unlike magnetic field, which has 3 components, the scalar field is in fact described by only one component. That means you have to just specify one function. Instead of specifying Bx, By, and Bz at every point in space, you have to specify just one variable at every point in space. So let's call that variable h. So this will be like having a particle at every point in space, but the particle moves in one hidden direction and not 3 hidden directions. Now, in quantum field theory, or even in classical field theory, the motion of such a field is controlled by a potential which plays the role of the height of the hill. So technically what happens is that if you consider a particular configuration of field, so that the field can take different values at different point in space, okay, we can ask what is the energy associated with such a configuration. Okay. And the energy expression for the energy is given by this. You integrate over space. Okay. There are 2 terms. One is a potential term. Okay. The larger the potential, the higher the energy density that it costs, the potential energy density. Okay. And then there is a gradient term. Okay. This says that if the field has a gradient, okay, then that also costs energy. Okay. So if you want to minimize potential energy, the potential energy, then you will try to minimize the gradient. And at the same time, you will try to minimize the value of the potential. This form of the energy is valid for time-independent field. Okay. If the field depends on time, then there is an additional term which plays the role of the kinetic energy of the particle. Okay, so now let's consider a form of the potential V with 2 minimum, just like we had in the case of particle. So if you have a scalar field with a potential like this, okay, then locally minimum energy configuration corresponds to when the scalar field is at A everywhere in space, okay, or when the scalar field is at B everywhere in space. Okay. So this can rest in either minimum. Okay. And we say that these 2 states of the universe, okay, represent 2 different phases of the theory. So here the word phases is used in the same sense as ice and water are different phases of H2O. Okay. The underlying dynamics is in both cases is described by the dynamics of H2O molecules, okay, but the realization is different. Okay, so in that sense, you can think of A and B as 2 different realizations of this underlying theory of scalar field. Now it turns out that the properties of these 2 phases are typically very different. Okay, just like the properties of ice and water are quite different. But the difference that comes in quantum field theory is even more striking, because even the properties of elementary particles, like the mass and charge of the electron, they'll be different in different phases. In fact, there may not even be a particle like electron in phase B, whereas there is a particle like electron in phase A, right? It may happen. So they are very different properties, elementary particles themselves. And in terms of this picture, you can also explain what dark energy means. So we talked about dark energy density in the context of expanding universe. But in this picture, dark energy density has a very simple interpretation. It's simply the value of the potential at the local minimum. So if, for example, the field is at A, field is resting at A, then the dark energy density is positive. That is what you see in our universe. Okay. If the field is resting at B, then the dark energy density is negative, which is not what we see in our universe, but there can be other phases of the theory in which this is the case. Okay, now let's ask what will be the effect of quantum mechanics. And so for this, let's again recall the case of particle on a hill. We have seen that if the particle is sitting at A, then classical laws tell us that it will sit there forever. But quantum mechanics tells us that there is a small probability that the particle can tunnel to B. Okay, it can just appear on the other side of the hill and then roll down to B. So given this, one can ask, can a similar tunneling happen in a quantum field theory? Okay, imagine that you have a scalar field with these two minimum. Okay. Can it, and suppose it's sitting at A, can it tunnel to B? Now the probability that it will tunnel from A to B everywhere at the same time is 0. Okay, because when you say the field is sitting at A, that means the field has a value corresponding to A at every point in space. Okay. And the probability that at every point in space, the field will suddenly tunnel from A to B, okay, you can show it's 0. But something else can happen. Okay, that imagine that the field corresponds to A everywhere in space. Okay, but it may happen that in a small region inside space, the field can tunnel to B. Okay, this has a finite probability. Okay, small but finite probability that in a small region, the field may tunnel from A to B. Now let's ask what will happen if such a tunneling takes place. Once a tunneling like this has taken place, then what will this bubble do? Now we know that everything tries to lower its potential energy, so the bubble will also try to lower its potential energy, just by classical dynamics. So B has lower potential energy density. So from that perspective, it's favorable for the bubble to expand, okay, because then it will lower its potential energy density, potential energy. But there's also a gradient. Remember that across this surface, the field has to change from B to energy, and that gradient energy will be proportional to the surface area. So as the bubble expands, okay, the surface area will increase. So that means the gradient energy will increase. So there will be a competition between these two effects, and the question is which one will win. And a simple calculation shows that as long as the bubble size is sufficiently large, then the surface tension can be overcome. Then you gain more, you lower your potential energy by expanding. Okay, it's true that the surface energy increases, but the gain in the potential energy, okay, or the loss in the potential energy is sufficient to overcome that surface tension. So once a bubble of this critical size is produced, this bubble will begin expanding, okay, because everything tries to lower its potential energy. So in that process, the potential energy will be lowered, but of course the energy has to go somewhere. Energy has to be conserved, and the only place that it can go to is in the kinetic energy of the surface. So the surface starts accelerating. Okay, this acceleration is of course very different from the accelerated expansion of the universe that we talked about. Here we are talking about the expansion of a quantum bubble. Okay, a bubble that has been produced by quantum mechanics. So what happens is that now the surface begins an accelerated expansion, and in that process it converts the potential energy difference to kinetic energy. And because of this accelerated constant acceleration, one can show that soon the speed of expansion of the surface approaches the speed of light, and eventually it converts A to B everywhere. So for this reason, this phase where the field is sitting at A is often called the false vacuum or the metastable vacuum, because this gives the impression of a stable lowest energy state, but actually this is not so. And you can also imagine an analogy of this in everyday life, and that analogy will be that of a supercooled water. Okay, you can lower the temperature of water below the freezing point if you cool it sufficiently slowly. Okay, but a small disturbance, okay, that can create a pocket of ice inside water, okay, will now start expanding. Okay, once a small pocket of ice is created inside the water, that ice ball starts expanding and eventually converts water to ice everywhere. So this is also a similar phenomenon. The phase A will be converted to the phase B everywhere in the universe. Now A could be a universe, a phase like us. So imagine that A had its own stars and galaxies and perhaps also living objects. And you can ask what will be the fate of these objects once this bubble wall hits it. And the answer is simple, that it will be total instantaneous destruction of anything that is living in A. And the reason is simple. Okay, the reason is something that I've already told you. Because the elementary constituents like the electrons, which would make up objects in A, do not exist in B. Okay, and even if something like electron exists, their masses are very different. Their charges could be very different. So they are not going to give rise to the same kind of objects that we see in A. So from the point of view of A, we can call it the killer bomb because it basically kills everything that it touches. So with this, we now turn to the central question of this talk. And that is, are we living in a false vacuum? So this possibility, of course, is not new. It has been known for about 50 years. But some recent developments have generated renewed interest in this subject, okay, as to whether we are living in a false vacuum. So one of these recent developments is the experiment in CERN in 2012, which discovered the first example of a scalar field in nature, of an elementary scalar field in nature, and that is called the Higgs field. Okay. Many of you probably have heard of Higgs particle. Okay, this Higgs field is intimately connected to the Higgs particle. So given that there is such a scalar field, we can ask, are we living in the false vacuum of the Higgs field? Now, when you write the theory of the Higgs field, okay, when it was written down in more than 50 years ago, people wrote down a nice form of the potential, which has a single minimum. You can see at H equal to B. Okay, take H to be positive. So it has a minimum at H equal to B. And our vacuum was described by the minimum at H equal to B. So if this was the potential, then of course we are living in a true vacuum. There is no other minimum. But it turns out that the quantum mechanics, okay, spoils the fun again. It actually creates more minimum. Okay, it actually modifies the form of V and produces other minimum. And if it so happens that those other minima are below the minimum corresponding to H equal to B, then we will be living in the false vacuum because those other minima will be more stable. Okay, we could tunnel to those other minima. So given this, it becomes important to know, are we at the true minimum of the corrected potential? Now here the answer is not completely determined yet, because it turns out that the quantum corrections depend on the mass of the top quark and other parameters of the theory. So at present, okay, within the current accuracy, it could go other way, either way. Okay, the other minimum we know is very close to ours. Okay, the energy of the other minimum is very close to ours, but it could be either slightly above or slightly below ours. Okay, we still don't know the answer, but it seems more likely that it's slightly below ours. But even if it's slightly below ours, and if you are living in a false vacuum, in this case, I think the probability that we will tunnel to those is so tiny that you don't really have to worry about this. But the actual situation turns out to be more complicated, because there are theoretical reasons to believe that there may be many more scalar fields in our theory. It's just that we have not had enough energy to discover them. And among these unknown scalar fields, there may be scalars whose false vacuum describes us. In fact, it's not only possible, but it's sometimes useful or inevitable from many various theoretical reasons. So let me just mention a few. Supersymmetry, it has not been discovered, but it is one of the postulates, okay, or one of the ways people try to make sense of what we see in nature today. So this has been useful in addressing many issues in particle physics, although it's neither necessary nor has it been seen. But because supersymmetry implies symmetry among the bosons and fermions, which you know is not present in nature, this symmetry must somehow be broken. And it turns out that breaking up supersymmetry is hard to achieve if we live in the true vacuum, but it's easy to achieve if we live in the false vacuum. So if indeed our world is supersymmetric, then it's much easier to reconcile that with what we see in nature if we accept that we are living in a false vacuum. Here is a completely defined mechanism for tunneling. In some theories which have higher dimensions, more than 3 space and 1 time dimension that we see, that turns out to be a cousin of false vacuum decay. So the mechanism for this false vacuum decay is similar, except that instead of having a new phase B inside, okay, there is nothing. Okay? The space-time doesn't exist inside B. Okay, it just ends at this bubble 1. And this is sometimes called the bubble of nothing. Okay? But as far as A is concerned, okay, the effect will be exactly what we saw earlier, the total instantaneous destruction of anything that's living in it. So now then let's turn to the question again, are we living in a false vacuum? And the only way we can know this for sure is if we have some fundamental theory. Which, now what do you mean by fundamental theory? That it seems to be physically impossible to actually do experiment and figure out all the scalar fields that we may have. Because there may always be danger that we have only got up to certain value of energy and there may be scalar fields which are lying beyond that energy. But if we have a fundamental theory which tells us from some first principle what is the list of fields and the potential that the fields have, then we could use that information and actually calculate to see if we are in the true vacuum or the false vacuum. And if you are in the false vacuum, what are the chances that will make transition into a true vacuum? So string theory is an attempt to have such a fundamental theory. It's a proposal for a theory that describes all elementary particles and their forces. And according to our current understanding, string theory has indeed many scalar fields. And these scalar fields have complicated potential with many local maxima and minima. And this is sometimes called the landscape of aqua in string theory. Okay, instead of having one scalar field, here I have drawn only one scalar, one direction. Okay? But you think of this as a multidimensional space, okay? A complicated function which has many ups and downs. And we hopefully are one of the minima in that landscape. So if string theory is right, then one of these minima describes the phase of the theory that we are living in. Now it turns out that we have found many phases of string theory whose elementary particles have properties that are very similar to the ones we see in nature. But the problem with string theory is that we do not yet know of a particular phase that describes exactly the elementary particles we see. So which means that even if string theory is correct, we do not know at present our position in the landscape. We are just one of these. Nevertheless, we are not totally in the dark. Okay, we know something about our position in the landscape. And that comes from these two observations. The first one is an experimental observation, the discovery of dark energy. That tells us that in the phase that we are living in at present, the potential is positive. Because the dark energy density is simply the value of the potential that at the minimum. So this we know for sure. The other fact that we know from theoretical studies in string theory, that while we have not identified the particular minimum that describes us, we have actually found many minima in string theory, and we can study their properties. And we know that it has many minima where the potential is either 0 or where it's negative. And this means that if string theory is right, then we must be living in a false vacuum, because we are at a positive value of the potential, and we know that the potential does have other minimum where the value is either 0 or negative. So assuming that we are living in a false vacuum, we can ask how likely is it that we will be hit by a killer bubble during the next 1 year. So if you want to answer this question, okay, it requires a two-part calculation. The first part uses quantum mechanics to calculate the rate of production of the killer bubble per unit volume, per unit time. So this part of the calculation requires knowing the form of the potential and the knowledge of our location in the landscape. It depends on whether you are here or here, okay, how far is the next minimum from us, okay, how high is the potential that separates between us and the next minimum, and so on. Okay. So it requires all this detailed information about the potential in our neighborhood. Okay. And because we don't know where in the landscape we are in, okay, we cannot do this calculation at present. So it's not possible to do this calculation today, but let's call this rate B. Okay, suppose B is the rate of production of these killer bubbles per unit volume per unit time. Okay, and once they are produced, they will start expanding at the speed of light. The second part of the calculation is something that we can actually do. So this is the space-time diagram that I showed you a few slides ago. Okay, this is what I call the conformal space-time diagram. Now, what is this diagram? So let's suppose that we are at time t, okay, and let's consider a small interval delta t. Now, what we do is that we draw this 45-degree angle from us back to the beginning of the universe. Okay, this is the t equal to 0. Okay, where the Big Bang happened. And similarly, we draw 45-degree angles from the point t plus delta t back to the beginning of the universe. And then we calculate the volume of this region. Okay, volume of the region that is bounded by these two cones. Okay, the volume of this, the space-time volume of this region. Now, why is this important? Okay, let's suppose that this volume I recall h of t times some function of t times delta t. This function of t that is something that you can calculate. Okay, it's calculable in terms of those functions f of t and g of t that I had shown you earlier. But let's try to understand why is this calculation important. Now, is this calculation important? Because imagine that we have a killer bubble produced somewhere here. Because the killer bubble surface travels at the speed of light, it will go at 45-degree angle. And if the killer bubble is produced somewhere here, it would have hit us before the time t. If the killer bubble is produced somewhere here in the white region on this side, then again it travels at 45-degree. So it will either hit us after the time t plus delta t, or it will not hit us at all, right? If it's produced sufficiently far, it will not hit us, okay, because it will be outside our horizon. But killer bubbles that are produced in this shaded region, those are the ones that are going to travel at 45-degree angle, okay, whose trajectories will follow this 45-degree angle, and those are the ones that are going to hit us between the time t and t plus delta t. So if you are trying to calculate the probability of being hit by this killer bubble between time t and t plus delta t, okay, is b times h of t times delta t. Okay, that's the way you calculate the probability. So b is unknown, but h of t is a calculable function. Okay, it's calculable based on our present understanding of cosmology. And here is the result that one finds. So the first result that one finds is that the h of t is actually increasing with time. Second, we can calculate today's value of h, and that turns out to be 3.7 times larger than the past average value of h of t. Okay, past average value of h of t is the average probability that the killer bubble would have hit us earlier than today. Furthermore, one can show that the value of h of t in the far future, okay, this is the asymptotic future, will be about 15 times larger than the current value. So one line summary of this analysis is that life in this universe is getting more risky. We don't know the actual risk because that requires computing B, but we know for sure that living today, okay, is more risky than living in the past, okay, because today we are more likely to be hit by killer bubble, and living in the future will be more risky than living today because the likelihood of being hit by a killer bubble will go up with time. But as I said, the theory cannot tell us the actual risk. So you can ask, can you invoke experiment? Okay, is there any experiment that could tell us what could be the possible risk of being hit by a killer bubble during the next 1 year? And for this, the only experiment that we have available, which is useful for answering this question, or at least partially answering this question, is our universe itself, the age of our universe. We know that our universe is about 14 billion years old. And this basically means that unless you have been extremely lucky, the risk of a hit per year must be less than 1 in 10 to the 10. Okay? Because it was much larger than 1 in 10 to the 10, we would have been hit by a killer bubble already. Okay? We wouldn't even exist today. So you can put a bound on how likely it is. Of course, the actual risk can be much lower than this. Okay? But we can say the risk is perhaps not larger than 1 in 10 to the 10. Now 1 in 10 to the 10 is a small number, okay, but we are not very familiar with large numbers. Okay, we can't always visualize large numbers. So you can ask, how small is this number? Okay, is there a way to get an estimate of how small this number is? And here is one to get an idea of how small the number is. Okay. So let's suppose that one day a small asteroid hits the Earth and destroys everything within 100-meter radius of impact. One can easily verify, okay, just by knowing the area of the Earth, that the chance that you will be within that region is about 1 in 10 to the 10. So it's a very tiny probability, but it's not unimaginably small. Okay, it's something that you can actually visualize. Well, I promised you some excitement in quantum theory, and I hope you would agree that the possibility, however small, that tomorrow you may be actually wiped out by a killer bubble, and the rest of the universe will follow suit, is perhaps more exciting than waiting for a slow death over billions of years. So now I'm going to turn to the last part of the talk, and that is the other promise that I had made, the promise of an adventure. Now, from what I have described so far, okay, life may be more exciting, okay, to consider this possibility, but adventure requires action, right? You can't just wait for the killer bubble to come and hit you and call that an adventure. So let's see whether you can actually have some adventure with this killer bubble. And it turns out that, as in most adventures, you actually need to leave home for having an adventure. So for this, let's recall some of the facts that we learned. So the first thing we learned, okay, that was in the classical part of the story, that at present we can access a certain region of the universe that is given by our horizon size. We also learned that with time, the expansion of the universe will convert this into a multiverse with many universes. And the rate of increase in the number of distinct universes is controlled by the expansion rate of the universe. So in particular, I told you that every 12 billion years, okay, the size of the universe will double. That means there will be about 8 separate universes will be created. That's 2 cube, which will not be able to communicate with each other. Okay, so these are really distinct universes. And when I say that they cannot communicate with each other, this also means that if a killer bubble is produced in one of these universes, it will not be able to destroy the other universes, because killer bubble travels at the speed of light, and even light cannot cross over to the other universes. So this was the classical story. In the quantum part of the story, we learned that killer bubbles are going to make some of these universes unlivable. And the rate of decrease in the number of livable universes is controlled by the function b times h of t. H of t is something that you can calculate, but b is something that you cannot calculate. But it's some rate, okay, some rate of decrease that we know we, in principle, will be able to calculate if we knew exactly where our position in the landscape is. So given these two competing effects, we see that if the rate of universe production exceeds the rate of destruction, then the number of livable universes will actually increase with time. If this happens, okay, this is the favorable circumstances. If this happens, does this help us? Now it turns out that it doesn't help us in any way if we are lazy. So if we remain confined within our galaxy, which will be within one of the universes, then our annihilation probability will be controlled by the rate of destruction. The fact that all these other universes are getting created, okay, are of no use. Now, of course, it's possible that this rate is small enough so that the killer bubble that will reach us after the galaxy has burnt its fuel, and we have perished anyway. So in that case, of course, you don't care. But it will perhaps be a pity if we perish when the galaxy still has a lot of time to go. Now, one way we can try to overcome this fate is if we spread out into a currently accessible universe, which is within our horizon size. Okay, there are plenty of galaxies within our horizon size, and in principle, it is possible for us to spread out into those various galaxies. Now, once we spread out into those various galaxies, over time, this region will split into many universes. These different galaxies will become part of different universes. And in that case, even if some of them are destroyed by the killer bubble, the others will survive. And this way, what we can do, we cannot extend the lifetime of any particular civilization, but we can extend the collective life expectancy of our civilization. Even if one is destroyed, there will be others which will live on. And one can do a quick calculation which shows that spreading into n universes increases the collective life expectancy by a factor of this. Now, this you can probably recognize as a non-convergent series. If n is large, if as n becomes larger and larger, this grows. So, in principle, by keeping on spreading into more and more of these universes, so you can extend our collective life expectancy indefinitely. But in practice, of course, there are only a finite number of galaxies, and so there is a limit. But we can see that even if we spread into one more universe, one more galaxy that will go out of our horizon, we can increase the life expectancy by a factor of by 50%. The first two spreading into two makes it 1.5 times the life expectancy of a single galaxy. So this is basically the story that I wanted to tell you about. Now, based on this story, you might be led to believe that, okay, we will do this and we will be the heroes. But let me remind you that it's not us who will be the heroes. The real hero is the dark energy. Without dark energy, there is no horizon or multiverse, and the single killer bubble is going to destroy the entire universe. It's the dark energy that is creating new universes at a constant rate. And all we can do is that we can try to spread out within our currently accessible horizon as far as possible. And then it's the dark energy that is going to pull us apart and make us part of different universes, which will save us from simultaneous annihilation by killer bubbles. So this brings me to the conclusion of the talk. So I have said many things, but I'm sure that by today evening, you will probably forget most of what I said. So I tried to make a one-sentence summary of this talk, which you might remember for a little longer time. And so here it is. And that is the dark energy helps those who help themselves. So with this, let me conclude. So stay safe and think of ways to populate the universe within our horizon. Thank you.
Let us thank Professor Sen for this magnificent delivery. Now, it is time to, I'm sure he will like to answer questions if there are any. I can't see any question in the chat box yet, but Kaushik, can you see any question in the, YouTube?
No, I still don't anything, so you may please take.
No, there is no question in the chat box yet, excepting some thank you message for Ashok. But first of all, if anybody wants to present a question, you are requested to type into the chat box immediately. Otherwise, you may take this opportunity to unmute and raise your hand, in which case you may be invited to ask your questions. Can people raise their hands if they have questions?
I can see some people raising hands.
They are not showing here. There is a question from Sayanho Biswas. So can you ask your question or type it into the chat box?
Can I ask it?
Please ask your question. Yes.
Sir, I won't take much of your time. I'm just a first-year student and I do not know absolutely anything about these things. But I'm very curious and I wish to know that what is the probability or what is the expectancy of obtaining an experimental verification for the string theory in the upcoming years?
Well, that's very hard to say. I mean, if you are lucky, we may find something. Right? I mean, the direct experimental verification requires creating strings, and that requires very, very high energy. Okay, that doesn't seem to be possible in the near future. Okay. But people are of course looking for various indirect signals, okay, like in cosmology, for example. Okay. And there it's more like hit and miss. You may find some signal, you may not. Okay. So it depends on luck. But if we really want to verify string theory, okay, by direct experiments, then it requires a very, very high energy accelerators, which you don't expect to build in the near future.
Thank you, sir. Thank you, sir.
Okay. The next hand is raised is that of Siddharth Lal. So Siddharth, why don't you ask your question?
Thanks for the wonderful talk, Ashok. I just was curious. Is there likely to be some kind of a condensed matter equivalent question to the scenario that you've proposed here? Something that can be perhaps tested in a tabletop experiment? I mean, an analog.
Yeah. So in condensed matter, of course, the one analogy I gave of this phase transition is the supercooled water, right?
Right.
That when ice starts forming, it just expands and fills water.
Right.
So that typically happens not by quantum fluctuation, but by some thermal fluctuation.
That's right.
Okay. But there are also quantum phase transitions, right? At zero temperature, which happen at zero temperature. So imagine that you have two phases like this. One is metastable, the other one is stable.
Right.
And there, it could happen that quantum fluctuations, that if you have a metastable phase, if you are in the metastable phase, then the quantum fluctuations can actually give rise to the stable phase which expands.
Right. It's just that I'm not able to figure out any analog for dark energy in any condensed matter system.
Yeah.
I mean, your scenario needs a competition between dark energy and the possibility of nucleation, I guess.
Yeah. So there is nothing, because the fact that dark energy gives this continuous expansion, that has no analog in condensed matter physics. But the one that you can see is the first part, the quantum phase transition.
Right.
The bubble B will expand and fill in.
Right. No, yeah. I mean that I'm familiar with. I was just wondering, the intriguing scenario that you have this negative pressure, which is competing with such nucleation processes, yes. The killer bubbles you're talking about, whether one can create some kind of an analog of this. And that's what I couldn't think easily of any negative pressure scenario that easily in a condensed matter system. That would.
Yeah, I also don't know. Yeah, I agree. That is the part which is very peculiar to gravity. That
right.
It gives rise to this accelerated expansion.
But if one had strongly repulsive forces, let's say, which would keep a system from contracting beyond a point, could that perhaps be useful?
Yeah, it could be, but perhaps it will still not be an exact analogy, because it will tell you that the expansion of these bubbles may stop at some point, right? It will not tell you that the volume, the metastable volume is actually increasing.
Right.
I think that is very hard to simulate in condensed matter physics.
Yeah.
I don't know the way to do that.
Right. Yeah. Thank you so much.
So that part seems to be very peculiar to gravity, that whenever you have metastable phases like this with positive dark energy, the gravity basically tells you that it will continuously expand.
Right. So it's this cosmological constant part of Einstein's equation, which somehow doesn't have any clear analog in a condensed matter system.
Exactly. That's right.
Right. Thank you.
Thank you.
Okay, there is a question in the chat box. Suraj Sharma asks, does the universe have a physical boundary? I mean, as we are considering the fact that the universe is expanding, then how can something without a physical boundary?
Well, it need not have a physical boundary. It can be either infinite, or it could be like the surface of a balloon, for example, which has no end. There are various possibilities people have considered, and we don't know if it is true or not. If it has actually a physical boundary, that could also happen. Okay, and the way it can happen is the following: that maybe I go to full screen mode. So in this picture, we are thinking of us as A, right? and the killer bubble as B. But it could even be that the universe that we are living in is actually something like B. That we may be expanding into somebody's some other universe. We may be more stable than this one. Okay, this may have even higher potential, and we are expanding into this. In which case, of course, if you are very far in the interior, you will not see this wall. But this wall will be some sort of physical boundary of the universe, right? That possibility also exists. So universe may have a physical boundary, may not have. We don't know the answer today. But the expansion of the universe doesn't require that it should have a physical boundary, but it could be simply like the surface of a balloon, which is blowing up. Okay, so every point in going apart away from everybody, every point, but the surface of a balloon has no boundary.
He says, thank you. I can't see any raised hand. Yeah. Okay, so as far as the chat box is concerned and raised hands are concerned, I think all the questions have been responded to. But Kaushik, is there anything in YouTube?
Vishwarupta, I can confirm that from the YouTube, there is no questions posted there.
There is no raised hand or chat box question either as yet. Okay, so anyway, so before we draw the session to a close, maybe one can wait for a minute or so in order to see if somebody has any impromptu question to ask. If any member of the audience wants to ask anything, please ask straight away to Professor Sen. Unmute your machine and just ask the question. Professor Paul, do you have a question?
No, I don't have a question. I just wanted to tell hi to Ashok.
Hello, yeah, how are you? Nice to see you.
So I hope you are in Bangalore now, right?
Yeah.
Great. Yeah, we, of course, I know him for a long time. So
Yeah.
good to hear you again.
Thank you. Yeah, I think I talked in Iceland about a year ago, right?
Yeah, about a year ago, right? About 1 year. I think Science
That was,
Day.
yeah,
Science Day, yeah.
Science Day.
28th February.
Exactly.
And he had also given a talk on Science Day at NCI.
Yeah, that's right, yeah.
Good.
Okay, so if there are no more questions, it is my pleasant duty to thank the speaker again. And of course, it is never sufficient to thank him given my nearly 30 years of association with him. So it's never enough thanks that I can give him for the amount of enlightenment I have received from him, and so have many of our colleagues across the community. So before we come to a close, I'll request Professor Anand Banerjee, the head of the Department of Physical Sciences, to make the concluding remarks.
Thanks, Vishwarupta. Yeah, so after such a talk, I think I don't want to waste too many words because I think people are probably allowing everything to sink in, because it's been a very interesting fusion, as it was wont, of course, fusion of quasi science fiction, which is, however, absolutely not fiction at all, but sharp, incisive physics, but which takes it's a great conglomeration of the human imagination, mathematics, as well as physics at its deepest end, which creates such wonderful stories. So yeah, Professor Sen had come to us first 1 year back, but after hearing such talks, one feels greedy that if he could come to us like every month or two with such great talks, phenomenal talks, it would really be so good for us. So anyway, it has really been a most appropriate, first talk for the Bibha Chowdhuri Memorial Lecture series that DPS has started. And we hope that Professor Sen would always be with us when we need him. And we would, of course, have loved to actually present this plaque that we've designed on this occasion. If we could have handed it over to him. Hopefully the pandemic has somewhat abated, so in the near future we can have him probably visiting our campus in person and illuminating us with beautiful stories like this. But then, yeah, all good things need to end. So again, I thank Professor Sen. I thank, of course, everybody in DPS who has contributed. I thank the members of the audience for having been there in such large numbers. This is now on YouTube, so I think everybody can hear this, even if they have missed it today. Professor Pal for taking out his very valuable time. I know he's immensely busy these days, but he's actually been through the talk. This really shows, enthusiasm for science keeps on, even if you're in administration. And I hope we would be able to carry on this legacy that we have commenced today, and we will have such speakers again, grace the occasion of the Bibha Chowdhuri Memorial Lecture. Thanks again. So I think we will bring the session to an end, and please, all of you, take care, stay in peace, take care of your health, and goodbye.
Thank you.
Thank you, Ashok.
Goodbye.
Wonderful talk.
Goodbye.
Bye, Ashok. I'll talk to you later.
Thank you.
Thank you, Ashok. Thank you.
Thank you.
Thank you.